Welcome to the deep dive. So we've been looking through these really interesting notes you shared,
Yeah.
and they point to this, well, pretty unexpected connection, a core concept from calculus class,
Uh-huh.
showing up in how we understand, of all things, the food we eat.
That's right. The source material really digs into how mathematical differentiation gets used to analyze something so, well, tangible, like food texture.
Okay.
So our mission in this deep dive is basically to unpack that link, how differentiation helps us quantify, how crunchy or smooth food is.
Right, the feel of it.
Exactly.
Yeah.
And maybe surprisingly, how this all connects back to food security. We want to make it clear, make it interesting, especially if, you're maybe a college student wrestling with calculus right now.
So the main idea from these notes is differentiation, derivatives. They're actually being used in labs to analyze food texture.
Precisely. It seems like these abstract math tools are kind of essential for measuring physical properties we experience every day. And what's really fascinating, I think, is moving from just saying, oh, this cracker is crunchy,
Yeah, the qualitative side.
to actually putting a number on how crunchy.
Yeah.
The research shows that's where these math concepts come in. It's about quantification.
And the notes don't stop there. They link this texture stuff directly to food security. How does that work? How does knowing how crunchy a cracker is relate to such a big issue?
Well, it's actually a pretty crucial piece. Think about it. Consistent, reliable food texture.
Yeah.
That's vital for quality control
Okay.
and for predicting shelf life, making sure food holds up during storage, transport, you name it.
Right, so it doesn't go bad unexpectedly.
Exactly.
Mm.
If a food's texture degrades too quickly, maybe it gets stale faster than expected, or I don't know, a sauce separates,
Uh-huh.
it can become unpleasant, maybe even unsafe, or just not meet the standards. And that leads to waste.
Oh, okay. Waste.
And waste directly impacts the availability and reliability of food in the supply chain. Those are like fundamental aspects of food security. So precise measurement helps prevent that loss.
Okay, so the math helps predict, maybe, when your favorite cracker stops being reliably crunchy.
Sort of, yeah.
And knowing that helps reduce waste down the line.
You got it. It's about consistency and predicting stability. Yeah. Now, differentiation, it's all about rates of change, right?
Right.
So how does measuring the rate of change of force tell you something specific about, say, that cracker we mentioned?
Okay. Thinking back to calculus, a derivative gives you the instantaneous rate of change, like how fast velocity changes at one exact moment.
Yep.
So for texture,
Mhm.
is it about how quickly the force changes as you bite down or press on something?
Exactly. Spot on.
Yeah.
Imagine some instrument biting into that cracker or maybe pressing down on some cheese.
Yeah.
It measures the force needed over time or over
Yeah.
distance.
Okay.
The rate at which that force changes as the food, deforms or breaks, that gives you the key data.
So the graph of the force.
Yeah. Think about the graph. For a cracker, you apply force, it builds up, and boom, it drops suddenly when it breaks.
Right. Fracture point.
The slope of that force curve, right then its derivative, especially how fast it drops right after the peak force. That's your number for brittleness. Or crispness.
Mm.
A really sharp, steep negative slope means it's super crisp.
So a high derivative value, or maybe a really steep negative one right after the peak, that objectively tells you how crunchy it is. It turns that feeling into data.
It does. And that's why differentiation is so useful here. It captures the dynamics of how texture behaves under stress.
Okay.
For something chewier, like say gum, you'd look at how the force changes over like repeated bites or compressions. Analyzing those rates of change at different points in the cycle using derivatives, again, gives you data on things like elasticity, chewiness. It's not just the maximum force, but how that force profile changes.
But wait, texture still feels so subjective when you're actually eating, doesn't it? How can just looking at force changes capture all the, nuances we perceive?
Yeah, that's a really good question. And you're right, human perception is incredibly complex. It involves taste, smell, the whole mouthfeel. What this analysis does is quantify the mechanical properties.
Yeah.
And while it's not the whole sensory picture, these mechanical measurements, the ones we get using differentiation, they provide an objective baseline. And importantly, they correlate very strongly with what people actually perceive. They're critical for consistent product development, for manufacturing.
So consistency is key.
Absolutely. This objective data lets companies make sure every batch of, say, chips or cookies has that expected texture, which, again, loops right back to quality control and, on a larger scale, food security.
Wow. Okay. So just to wrap up this deep dive there, we've seen how these mathematical tools, differentiation, derivative stuff you might be learning right now in calculus,